Assalamualaikum and hi, my name is Ainur Athikah Binti Zulkeflee. My final project is related to nuclear physics and basic general relativity. The title is GW170817 Binary neutron star event constrained to nuclear matter equation of state. The supervisor is Dr. Mrutunjaya Bhuyan. The objective of this project is to study the physics and structure of neutron stars from its basic formation until their mergers, and also to study the nuclear matter, neutron star matter, and neutron star major constrained to the equation of state. The neutron star is the densest matter in the universe with a mass of at least 1.1 solar mass. It's shown that they are super dense because twice of the mass of the sun is squeezed into a star. The upper limit of the neutron star's mass, also defined as Oppenheimer-Zulkeflee limit, is around 2.1 solar mass, but a recent estimation of the upper limit is 2.16. If the mass of the neutron star exceeds the tip of the limit, then the neutron star will turn to a black hole. The formation of the neutron star is generally from the supernova explosion of a massive star together with gravitational collapse. So we can say the dying of the large stars is the birth of neutron stars. When two neutron stars merge, it will release a short gamma ray burst and a strong source of gravitational waves. Astrophysicists have been interested in binaries consist of neutron stars and black holes for a very long time. This is because they impact a lot of significant constraints for models of massive star evolution and compact object formation. The gravitational wave release is observed by physicists by using the laser interferometer gravitational wave, which is called LIGO. So the first detection of the gravitational signal produced by colliding two neutron stars is on 17 August 2017, which the signal is called GW170817. The signal was detected by the two identical LIGO detectors, and the information on improvement in localizing the cosmic event was obtained from the Virgo. The very first detection is a big opportunity to study deeper about the neutron stars and transform the understanding of the working of the universe. Managed to do the data extraction and draw plotting to study the nuclear matter, neutron matter, and neutron star merger. Data Mrutunjaya Bhuyan provided 5 sets of data which have different symmetry energy and compressibility to study energy sets of data including energy density, pressure density, mass lambda, radius, and density over saturation density. For nuclear matter, the graph involved are pressure density versus density and symmetry energy. For the graph pressure density versus density, in the x-axis here is rho over rho naught, where rho is mass energy density with formula rho equals to epsilon over c squared. The epsilon is the total energy density including rest energy of the metal constituents, and rho naught is the saturation density. The value of the saturation density is constant, which is 0.17 femtometer per cube. From this graph, we can see the side with higher symmetry energy shows higher pressure density. Pressure has to be continuous in the stellar interior and steadily increases with increasing depth. Note that above 10 to the power of 4 gram per cm cube, atoms will be fully ionized and forming a plasma of nuclei and electrons. For the shaded bands here were extracted from a paper by Lutra, Lorenko, Avancini, etc. in 2015, where in the mentioned paper, the flow experimental data is compared with results obtained for symmetric matter. The range of rho over rho naught for the band region here is between 2 and 4.6. We could say that neutron stars are predominantly composed of neutrons and more accurately of nuclear matter with a very large neutron excess compressed by a long range of gravitational force. The symmetry energy reflects the variation of the binding energy of the nucleons in the nuclear matter in function of its neutron to proton ratio. So here is the 5 sets of data where the band constraint here was also extracted from the same paper as before, which is Lutra 2014. The band constraint here is labeled as mix 1A, where the limit is between 25 and 35 megaelectron volt. So this is why we can see here only 2 datasets are compatible with the range, where others are above 35 megaelectron volt. And that is the tidal deformability parameter. This graph shows that lambda decreases with a large power of m. As for the neutron star matter is related with the mass versus radius graph. Referring to the graph here, the horizontal bands were extracted from this paper shown. The observational constraints from J1C14 to 230 mass measurement. And the similar measurements for two other millisecond pulsars, which is G1903 plus 0327 and G1909 plus 3744, which is the range of observed masses for double neutron star binaries. The corresponding mass radius curve are plotted alongside the bands that represent astrophysical constraints of the order of 2 stellar mass under stellar masses. None reach the maximum constraint here because the value of the solar mass of the constraint is 1.97, while the nearest value of solar mass from the provided data is only 1.9 solar mass. EoS is important to model compact astrophysical objects. It depends on the particles present in the matter and the forces acting among them. The interior of a neutron star contains nuclear matter in different states. The nuclear matter changes with increasing depth below the star surface. Mass and radius can strongly constrain the neutron star matter equation of state and rule out theoretical models of their composition.